So a little review of where we left off. We had this equation to calculate confidence intervals based off of whatever sample evidence we find. So we go out, we take a sample, and calculate the sample mean. That's the best guess that we have about where that true population mean is, right? So we know our sample means will be centered around that, even if we don't know what that value is, right? Sometimes we take a sample and I see a sample mean over here, maybe over here, maybe over here. And we then said, if I build these confidence intervals around these different sample mean values, that whatever percent of the, I choose a percent confidence, so 90, 95, 99, whatever confidence interval I'm building, there's that percent chance that my confidence interval will include that true population mean. Now, there are going to be times where I see really, sample means way out here. And if I build a confidence interval around that, it doesn't include that true population mean. Right? So if I'm saying something with 90% confidence, that also means that I'm wrong 10% of the time. Right? So that was kind of the idea that we had behind this. Another way to think about this as well. So I have an equation for the standard deviation of my sample mean, which is the square root of the original variance the data I sampled from, over my sample size. So I'm going to take that sample statistic. I'm going to go a certain number of standard deviations to the right, get my upper bound, and then a certain number of standard deviations to the left, or subtract that margin of error to get my lower bound. So we can do the exact same thing. I can find where we do the exact same thing, but with sample proportion. So here is kind of our setup for our sample mean. We have the sample proportion. Remember, we know the mean of our sample proportions is centered around whatever that true population proportion is. So if I'm flipping a coin, the true population proportion would be 0.5. We also had an equation for the standard deviation of that sample proportion. So just like with a sample mean, we know our sample proportion should be centered around whatever the true population proportion is, just like the sample means centered around the true population mean. Right? So if I then flip, let's do the coin flip example. Let's say I flip a coin 20 times and 11 of the 20 come up heads, right? So I see a proportion that's a little bit above 0.5. I then flip another 20 times, maybe I see 6 of them come up heads. So I see a sample proportion over here. Well, the same kind of idea would be true if I could build confidence intervals around those different sample proportion values. Whatever level of confidence I've chosen that percent of the time, my confidence interval will include that true population proportion. And then, alpha percent of the time, I'm not going to have a confidence interval that includes that true population proportion. Okay? So it's the same setup, right? So we're going to do the exact same thing, which is I'm going to take my sample statistic. I'm then going to add a certain number of standard deviations to get my upper bound, subtract a certain number of standard deviations to get my lower bound. Right? How many standard deviations away do I need to go? Well, we said that was whatever z value, gave me alpha total outside my interval. Or I've got two sides right to my interval, half of alpha in each tail. So it was the number of standard deviations, or the z value, that corresponded to whatever alpha over 2 we want in the tail. Remember, alpha was dictated by the level of confidence. 90% confidence, alpha was 0.1. 99% confidence, alpha was 0.01. Now here, I can multiply by that standard deviation of my sample proportion, but I have an equation for that, right? So usually what we were doing was we're taking the population proportion times 1 minus the population proportion over my sample size. Okay? So I can use that, but then I quickly see a problem. So I'll write that out. Just kind of substituting that formula in there. But remember, the whole point of these confidence intervals, I was using my sample proportion to figure out where the true population proportion is, because I don't know what it is. I don't have that data. So how can I use it in my confidence interval? Well, that's what the variance should be. We're going to use our best guess. We're going to estimate that with, we don't have our population proportion. The best guess that we have of what it is will be based off of our sample proportion. Sample proportion. There we go. So we kind of end up with this confidence interval equation. If I want to write it all out in one line, it looks something like this, right? But really the format's the same, right? I take my sample statistic, go a certain number of standard deviations to the left and the right. That's the number of standard deviations the way I need to go. I then need to multiply that by whatever the standard deviation actually is. It's just here, I'm looking at the standard deviation of a sample mean. Here, I'm looking at the standard deviation of my sample proportion. So slight differences there, but really the same kind of principles, right? It's set up the same kind of idea about what we're doing with these confidence intervals. And then here I've kind of already been referencing this thing that we're adding and subtracting as the margin of error. It's actually appropriate to use it when we're talking about proportions. Like I said, it doesn't really matter for the sake. I think it's easier just to always reference that as the margin of error. But if you have to talk to a statistician, they may not like it if you don't use it in regards to proportion. Okay. So we got kind of a confidence interval equation. We can start to think about, now I can look at some data, right, some sample evidence, and figure out what a true population proportion is. So let's do this example first. So let's say I do this survey and I find that 63 out of 81 people are in favor of healthcare coverage that covers pre-existing conditions, and I want to build a 99% confidence interval. Okay. So here I'm not directly given my sample proportion, but how could I find it? If I want the proportion of people who are in favor of covering pre-existing conditions. Yeah, 63 out of 81 people, right? Or I think this is like 0.78 or 0.77, somewhere around there. So sometimes I'm not directly given, this is some of the Connect homework problems even. We're looking at problems with proportions. They might not directly give you the sample proportion, but if they tell you this many out of this many, well, you can, 63 out of 81, 63 over 81, that would be your proportion. I know the number of people who respond in a certain way. I also, know the proportion. I simply divide by the total number of observations that I have here, 81. Okay. Questions on that idea? So we got our sample proportion. We've got our sample size. That's just 81. I've everything I need to plug into this equation. The only thing I need to do is look up that z-value. So if I want the 99% confidence interval, what is my alpha value for the total area of my tail here? %. Yeah, 0.01. There's 1% outside my interval, decimal form 0.01. Well, that means I've got half of alpha in each tail, or 0.005. Okay. So I'm then going to go to my table, right? When we're doing confidence intervals, and I'll go into this a little bit more in a second, but we're using the inverse process. We know the area in the tail that we want, right? 0.005. Okay. We know the area in the tail, and we want to find that corresponding z-value. So the area in the tail, or the cumulative probabilities, are what's here in the middle, right? The row and column headings, those are my z-scores. So I don't have a z-score. I'm trying to look up to find what z-value I want. So I know that the alpha over 2 value I have is 0.005. So I start to try to find that. Looks like I'm in between these two. So that would correspond to a z-value of negative 2.57, negative 2.58. We'd use the higher of the two. Now notice, when I look up alpha over 2, I'm always going to find that negative z-value, right? Because I'm always going to be on that left side of the distribution. I can kind of ignore that negative sign because it's already built into my confidence interval equation, right? This is the number of standard deviations the way I need to go to get my lower bound, right? 2.58, subtracting that. I then go 2.58 standard deviations above or add that to get my upper bound, right? So I can kind of ignore the negative sign. But I'm always going to, if I'm looking up alpha over 2, I'm always going to be looking at this left side of the distribution. I'll find the z-value I want. It'll just have a negative sign associated with it, right? When I actually go to plug it into my equation, I just need to use the absolute value, right? I can kind of ignore that negative sign. So once I have that, I've got all the pieces I need. It's just a matter of plugging everything in, right? I've got my z-value. I can calculate, this is probably the best way to do it, is to do these intermediate calculations. So instead of doing all this at once, I'm going to find the standard deviation of my sample proportions first, then I'll just have one value to plug in. Okay? So I plug in my sample proportion, my sample size, and I get the standard deviation of my sample proportions about 0.046. Now I've got just 3 values to plug in to that. Pretty basic. I mean, this is not too bad. It's take a number, add a number times another number to it, right? So it shouldn't be too tricky to get our calculators. We add either upper bound, we subtract the margin error, either lower bound. Any questions over any steps or part of the process here before I keep going? So, how do we use these confidence intervals? Well, in this case, I could say with 99% confidence, the true proportion of people who are in favor of covering pre-existing conditions is somewhere between what, 0.66 and 0.9. So way more than half of the people, right? If I'm trying to push this policy forward based off of my sample, I'm pretty confident that the public's going to be behind us, right? And the true population proportion of people who will be behind is somewhere between what, 66 and 90%, right? So that'd be pretty good. So, we can rule out kind of anything outside of that range as well. With 99% confidence, if I'm saying the true proportion is somewhere in this range, I can conversely say it can't be outside of that range, right? Kind of those two things are just different way of saying the same thing. But I think I want to make a point before we keep working through more examples, because I had someone in my office and I thought this was a good question. And I thought I probably should have thought of explaining it this way originally. So we use that Z table in 2 ways, right? One way, the very first way that I showed you was, okay, look, if I tell you a Z value, so let's go. Two columns here. If I tell you a Z value of -3, you could look that up on the table, or if we think about we don't have a tables, I could integrate that function and always find that cumulative probability. So I don't know, this is like 0.001, something like that. I then go to another Z value, right? -2.5. I could integrate that function, find the area to the left of that, right? So 0.006, I think. No, 0.006, around there. I could then do that for a bunch of different Z values. In fact, what if I did it for the Z value of 0? What should the area to the left? If I have a standard normal distribution, I know that it's centered around 0. So the cumulative probability, or the area to the left of a Z value of 0, should be what? Yeah, splits the distribution in half, so 0.5. Right? So now this is like a more simple way. I think it might seem more simple than using the table that we're using, and I'll explain why we have to use why we have the table that we have. Really, all we're doing is looking up a Z value. If I had this table, like let's say instead of like these big jumps, I did like -3, -2.99, -2.98, -2.97. I like made all these values. I'd have an insanely long table, right? But if you told me a Z value, I could tell you the corresponding probability. Any Z value you tell me, I would have kind of a corresponding probability over there on the right-hand side. Right? Conversely, or inversely, when we do the inverse process, it's where we don't know the Z value. We know the area that we want in the tail, and then we can find the corresponding Z value. Right? So we're just basically, it's like you have these pairs, right? All these Z values are always going to have the same probability, the same cumulative probability area to the left. So if you wanted to, you could write them out as like this really long list. It's just, that's not a practical table, right? And so to make it a little bit more condensed, to make it a little bit more practical, that's why we have kind of this system where we set it up, not just in these 2 columns, but kind of a column and different rows. Okay? But really the base of what we're doing is we're looking up a Z value that's always going to have the same area to the left. Or if we're doing the inverse, if we know the area to the left, it's always going to correspond to that same Z value. I don't know if that helps people the way they're thinking about it anymore, but I don't know. I think this maybe helps a little bit, at least some people. Any questions on this before we keep moving? So that's really what we're doing with confidence intervals. We're using the inverse process, right? We are always going to know the area we want in the tail is always half of alpha, right? So we always want the same area in the tail. We want alpha over 2. We're going to look that probability up, find the corresponding Z value, or use the inverse process. Okay. So let's do another one here. So let's say, this one I think should be kind of interesting. So let's say that I wanted to start to do like election predictions, right? So I've got the 2016, I also have 2020, which I don't think we'll get to it today, but maybe I'll review it a little bit on Friday. So in the 2016 election, there was a survey of 912 people, and we had 46% said they were going to vote for Clinton, right? Or a sample portion of 0.46, right? Our sample size, 912, right? And we wanted a 90% confidence interval. So my alpha is what? 0.1. Yeah, 0.1. Well, notice I've got everything I need except for the z-value, right? I can already plug everything in. I've got my sample portion, I've got my sample size, right? So the only thing left I need to do is figure out, well, what's this z-value, right? That would give me a total of 0.1 in the tails. Well, I've got two tails, so there's half of alpha in each tail, or an area of 0.05. I'll look that area of 0.05 up on my table, find the corresponding z-value. Okay. Now, just to kind of compare what we did before, I think before, with a 99% confidence interval, we had a z-value of 2.58. So if I've got a 90% confidence interval, what should be true about my z-value? So the area I want in the tail is 0.05. In our earlier example, we wanted 0.005. So that z-value was negative 2.58. I should find something a little bit smaller than that. Right? Now, then I have to use the table to look up what the actual value is. But I know the area I want in the tail, half of alpha, was 0.05. I scroll down here. Looks like I'm in between these two values. So that corresponds to a z-value of negative 1.64 and negative 1.65. Okay. So just for the sake of rounding, I'll use the higher of the two. So we've got, where did I put my, there it is. So negative 1.65. Well, now I've got everything I need. Plug in that z-value, plug in my sample proportions, plug in my sample size. Right? Now I can break it down to steps, right? I can calculate the standard deviation ahead of time. That way I just have one value to plug in. But the process is really, once I find that z-value, it's just a matter of calculating that standard deviation for my sample proportions, right? Plugging in the sample portion of 0.46 and the sample size of 912. Now I just have three values. It's a pretty big, pretty easy equation. I subtract my margin of error to my lower bound, and then add that same margin of error to get my upper bound. And part of this is just going to be practicing and working on and doing them. I'll probably get the next Connect assignment up. Just so if you want to, you can start kind of chipping away at these confidence interval questions, getting some more practice, but same steps every time. And so you're going to notice, like, if I'm doing the 90, 95, 99% confidence, I'm going to keep finding the same z-values. That's why I had these here. Like, anytime I want the 90% confidence interval, I'm always going to find that a half of alpha corresponds to the z-value of 1.25. Anytime I want the 99%, I'm always going to find that half of alpha, corresponds to a z-value of 2.58. So you'll see these numbers start popping up a lot, right? They might start becoming a little bit more familiar with them. But I want to do two things. So first thing, so I've got my confidence. With 90% confidence, I can see the true proportion of people who were going to vote for Clinton in 2016 was between 0.4328 and 0.4872. Okay. Notice I get a pretty narrow range. I mean, what, 0.0, not even 0.05 about, right? So I'm getting a pretty narrow range for these proportions, but that's because I took a really high sample size, right? I had 912 people. If my sample size is pretty large, what's going to be true about my standard deviation of my sample proportions? Well, if the denominator is getting larger, it's going to get smaller. If I'm adding and subtracting a smaller amount to my sample statistic, I'm going to be getting a narrower range of values. So by increasing that sample size, I'm decreasing the standard deviation of my sample proportions, decreasing my margin of error. And so I'm going, not quite as far out to the left and the right to get my upper and lower bound. These high sample sizes give you these narrow and intervals, which is good. The whole point of what we're trying to do is we're trying to pinpoint down, based off of our sample evidence, where's the true population proportion, right? I've got my sample proportion, and hopefully I can kind of pinpoint down and guarantee that the true population proportion is somewhere in a pretty narrow range of values. Any questions on that idea? Other thing I wanted to mention here was, I'll hold off on that. So we've got this confidence interval. There's something we can do that's kind of useful now, right? So let's say I've got this confidence interval for the proportion of people voting for Clinton. I then do the exact same thing, but I do it for Trump, right? So I have the same survey, the same people. I had that 40%, so they were planning to vote for Trump. So I've got my sample proportion of 0.4. I plug that in, sample size, get that standard deviation by sample proportion. I'm doing a 90% confidence interval. So if I'm doing 90% confidence interval, alpha is still going to be the same. Half of alpha in my tail is still going to be the same. I'm still going to find that same Z value. So I've now got my confidence interval at the 90% level for the proportion of people who are going to vote for Trump. So I can think about it like this. Right? This is what, 0.3732, 0.4267. Right? So with 90% confidence, I can tell you the true proportion of people voting for Trump is somewhere in this range. I then look at Clinton's. There we go. And this was what? 0.4328 and 0.4872. So the true proportion of people who were going to vote for Clinton was somewhere in that range. Right? So with 90% confidence, what could I say here? Well, even if it was the worst case scenario, and the true population proportion of people voting for Clinton was my lower bound, right? I know it's somewhere in this range. Let's assume it's the lowest possible value. I then could say, well, even if Trump had the highest possible value in my confidence interval range, what I could say with 90% confidence is that the proportion of people voting for Trump is still less than the proportion of people who are going to vote for Clinton, right? If there's no overlap in these confidence intervals, then even under the worst case scenario, I know that this group, if I could, this is Trump, Clinton, but whatever these two comparison groups are, this group is going to have a higher proportion than the other group. So here, with 90% confidence, I could say that Clinton was going to get a higher proportion of the overall votes, which it's ended up what having it shouldn't win, but it ended up with a higher popular vote. We can make predictions on the popular vote pretty easily just from like a survey as simple as this, right? Just asking, who you plan to vote for, take those sample proportions, these confidence intervals. Okay. Any questions on that idea? And extend it here. So let's instead, what would happen if I wanted to say something with a higher level of confidence? So I go from 90 to 99% confidence, right? What happens to my alpha? It's getting, so not 90% alpha is 0.1, 99% alpha is 0.01, so it's getting smaller, right? So my alpha over 2 value that I want in the tail is going to be smaller, which means I'm going to have to go a higher number of standard deviations away to build that confidence interval, to get that desired alpha over the 2 in the tail. So at higher levels of confidence, my Z value is going to get higher, which means my confidence intervals are going to get wider, right? So if I wanted to make this prediction with 99% confidence, well, I know that my confidence intervals, they're based around the same sample proportion, but they're going to be wider, right? So if I go to 99%, it's likely that my confidence intervals look something like this. Well, now they overlap, right? Now there's values, like I could potentially see the proportion of people voting for Clinton be here, and the proportion of people voting for Trump be here, in which case I predict Trump would win the election. But it could be that the true population proportion for Trump is somewhere down here, and the population proportion of people who vote for Clinton is somewhere up here. So anytime I have the overlapping confidence intervals, I can't make any statements, right? At least with that level of confidence, I can't, say one group is going to be higher than the other. But if they don't overlap, that's where I can start to make some pretty interesting statements. Okay? Questions on this before we keep on moving here? So I think I've got these 2020 election ones. They're really just different numbers. It's a similar kind of example. Might be some good practice if you want to try to kind of go back, try to reproduce these, kind of make sure you're doing practice using your calculator to figure out this upper and lower bound. But really it's the same thing, right? 90% confidence. I'm going to keep using that same Z value, right? Alpha is going to be the same. Alpha over 2 would be the same. So instead what we're going to do, and I did this for the last class, so I'm going to have to delete all of my work real quick so that it looks like what you download. So there we go. There's this YouTube dislike data set on Canvas, right? So this is going to be everything that you need to finish the Excel homework we're going to do right now. Right? So I had this, it's like, I don't know, popular YouTube accounts and then their videos, and it has like the number of likes, dislikes, a bunch of other stuff. So let's just use the likes variable for right now, just for the sake of this example, right? So maybe I want to know, what's the true population mean number of likes on these videos, right? For whatever reason, I'm working for some social media company or something like that, or ad agency, or I'm interested in how many eyes are on this thing. Sorry, I'll do my sample mean and my sample size, right? So I'm going to create kind of 2 places for that. How do I find my sample mean? Just my average function, right? So I go over, Control Shift, Command Shift on a Mac, hit the down arrow, hit Enter, right? Got my sample mean likes, right? I could then find my sample size by simply using the count function, right? We've done this with a lot of different stuff, right? Control Shift, hit the down arrow, then hit Enter to get out of the cell. So I've got my sample mean and my sample size here. The next thing I'm going to do is I'm going to think about, okay, look, I want to build 3 levels of confidence, right? 90, 95, 99%, right? So I've got this sample mean. I want to build 3 different confidence intervals, right? That's going to correspond to an alpha of what? 0.1, 0.05, and 0.01. You'll see why I'm setting it up this way in a second. So when we're looking at this confidence interval equation, I've got my sample mean, I've got my sample size. This is one of those we have to walk before we can run. Assume that we're somehow given our known population standard deviation, right? So we have a known population standard deviation. The only other thing we need to do is find the z-value that corresponds to having half of alpha in each tail, right? So that's what I'm going to look up in this column. So anytime we want a specific area in our tail and we want to find the corresponding z-value, we're using that standard normal distribution. And I said earlier, we're using the inverse process, right? So we actually already showed you how to use this function in earlier examples. It's just now we're going to use it again for confidence intervals, which is that norm.s.ind function, right? We're going to tell it the area we want in the tail. It's going to spit back out at us the z-value that gives us that area. Well, what area do we want in the tail? Alpha divided by 2, right? So this should give me, right, the z-value that corresponds to having half of an alpha of 0.1 in the tail. I'm going to copy that down and get the z-values I need for the next 2 levels as well. Okay. So I hit Enter, and then I'll drag this down. Okay. Now, one issue is going to be that when I'm looking up alpha over 2, I'm always going to find a negative z-value, right? Because I'm dealing with the, how many standard deviations below I'm going to get my lower bound. When we're actually using Excel to be our calculator, those are kind of already built into our confidence interval equation. So I just want the absolute value, right? I just want the same value, but without a negative sign. So one easy way of doing that is you can just use the ABS or absolute value function, right? That's just going to drop the negative sign for me. Okay. Show you a different way of doing it here in a second, but this is probably, I think, for most people, the easiest way, right? I know that I just want the z value. I don't want it, don't want it to be negative. So I copy that down. Now I've got the same 3 values, but now they're, they're not negative. And notice for the same thing that we were finding in the table, they're a little bit off because we don't have to round. 1.65, 2.58, right? That's what we were rounding to earlier. And then that'll be 1.96. So we're always going to find those same 3 z values when we're building these different confidence intervals. I could then create 2 columns, one where I find my lower bound, another where I find my upper bound. Okay. How do I find that lower bound? Well, I'm going to actually do something I think is a little bit easier. which is I'm going to calculate the standard deviation of my sample means ahead of time. Right? Can I do that intermediate step? So I'm going to go back up here. Standard deviation of my sample mean is just the square root of my population variance. Well, I've got a population standard deviation, so I need to make sure that I still square that, right? And then divide that by my sample size, right? So I'm just calculating this ahead of time so I can just select on one cell, right? Just breaking it down into steps. So my lower bound here, all I'm going to do is use Excel to be my calculator. What do I want? I want to take the sample mean, right, which I've got up here. I want to subtract whatever the z-value is that corresponds to alpha over 2 in the tail, multiplied by whatever value the standard deviation is. That's all I need to do. Just use Excel to be my calculator there to get my lower bound. Now, when I copy this down, there's going to be some issues. When I want to build different levels of confidence, I'm still basing it off of the same sample mean. My sample size hasn't changed. The only thing that should be changing is the number of standard deviations where I need to go. So when I want to build these different levels of confidence, if I copy this down, it'll update all my cell references. The only cell reference I want to update is the z-value that I'm using. So I'll go in, and every cell reference, the one for the sample mean, the standard deviation of my sample mean, I'll freeze those. Now when I copy this down, it should give me my lower bound for 3 different levels of confidence. Okay? So I'll hit enter. Oops. Scroll down. I then want to find my upper bound. It's the exact same equation that I just typed in. What's the only thing that changes? Yeah, instead of subtracting my margin of error, I add it. So instead of dragging this over, it'll update that cell reference for the z-value. If I double click on a cell, I go in and I copy, hit enter to get out of the cell. And you can use the shortcuts too to do this. And then I paste. Should give me the exact same number. When I copy and paste a formula, instead of dragging it over to copy, it doesn't update any of my cell references. And that's kind of nice because now I've got the same exact equation I had before. We said the only thing that's going to change is I'm adding my margin of error instead of subtracting it. Right? So you could type it all out again if you wanted to. That's fine. It's just kind of showing you a shortcut. You could just copy and paste that formula. It doesn't change anything. You didn't want anything to be different. The only thing you wanted to be different was you wanted to add the margin of error. So then just go in, change that negative sign to a positive sign. Any questions on that? You want to see a cell again or? Yeah. Yep. So we're just using that norm.s.inv function. The area we want in the tail is half of alpha. So I just selected on alpha divided by 2. And then we said we just want to drop the negative sign. So that's why we put the ABS or that absolute value on the outside. Yeah. Yep. Yeah, so all we're doing there is taking our sample mean, subtracting however many standard deviations away we need to go, times whatever the standard deviation was. Questions on this? See something again, or I want to see a different cell. All right, so notice what's happening to my upper and lower bounds when I want to say things with higher levels of confidence. We said before, higher levels of confidence should increase our z-value, which sure enough they do, which means my lower bound is going to be getting lower and my upper bound is going to be getting higher. Right? I'm getting wider ranges of values. Another kind of interesting thing is, notice my standard deviation is still pretty large, right? So even though I have a huge sample size, 37,000, right? So you would think, really high sample size should decrease that standard deviation and make my intervals pretty narrow. The problem is our population variance is really large here. I mean, the standard deviation is 525,000. So square that, and that's our variance, right? So even if we have really large samples, if the original data has a lot of variation in it, it's going to be hard to really get a kind of narrow range of possible values for a confidence interval. Okay? All right. Any more questions before we keep moving here? So this would be how you build a confidence interval when you have a known population standard deviation. I'm going to cheat. I'm going to, yeah. Yep. So I'm going to cheat and copy that whole table and paste it down here just so I don't have to type everything out again. No, wait here just a second. So the next thing that we're going to do is we're going to build confidence intervals, very similar way, but do it for a sample proportion. So the variable that we're going to use is I have this 1, 0 variable, which is, did the video have more likes than dislikes? So we said when we have a sample proportion, so I'm just gonna, I copied that table. I'm gonna, oh, let's try it again. I copied it. All right, I pasted it. I'm gonna get rid of these. Oh, maybe. There we go. So now I'm gonna find my sample proportion. I could find my sample size, assuming we didn't have some previous work already done. All a sample proportion is a unique case of the mean. So we're going to use the average function, and then we're going to find the mean or the average of a 1, 0 variable. So I'm going to select this more likes than dislikes variable, hit enter. Sends me back up to the top. I can use the count function once again. There we go. Control Shift, Command Shift on a Mac. Hit the down arrow, hit enter. I've now got my sample size and my sample proportion. So I've got my sample proportion, my sample size. The only thing left I need to do is look up those z-values. Now, so I'm going to do the intermediate step here ahead of time before we get too far. So instead of trying to type all this into Excel, I'm going to calculate this ahead of time, right? That's standard deviation of my sample proportions. So this is just going to be the square root of my sample proportion times 1 minus that sample proportion, and then divided by my sample size. Right? All I'm doing is having Excel be a calculator for me here, kind of calculating this intermediate step. You don't have to. You can do this all in one cell. It's just more parentheses, and it's easier to make a mistake. I think this is just kind of an easier way of setting it up, having it, that standard deviation of your sample proportion just in one cell. Now there's just 3 things to select when I'm finding my upper and my lower bound. Okay. So my z values should be the exact same as what they were before. My alphas are the same. I'm still using the standard normal distribution. Alpha over 2 will be the same. I'm going to use the exact same thing. I'm just going to show you a different way of finding those z values. So notice, if I have, I'm looking for these z values that give me half of alpha on each side, right? Problem was when I looked up alpha over 2, I was getting this negative sign. I had to use the absolute value. It was kind of a pain, right? Well, there's another way. What if I wanted to find it's that same z value, but positive, right? Well, I know that there will be alpha over 2 in the upper right tail, which means what would be the area to the left of this z value? This would just be 1 minus alpha over 2, right? So I know if I look up the area to the left of 1 minus alpha over 2, that should give me the same z value, but positive, right? So I can prove this to myself using that norm.s.v function. Tell it the area to the left is 1 minus alpha over 2, right? So this is going to look up 1 minus alpha over 2, tell you the z value. It should be the exact same thing as what we were finding up here, right? It's just a different way of doing it. If the absolute value way makes more sense, by all means do that. It kind of lines up a little bit more with how we do that by hand. But I just want to show you there is another way of doing this to kind of get that positive z value and not have to worry about the absolute value function. Any questions on that before we keep moving? Yeah. This guy? Yep. Yeah, so once again, just using Excel, kind of be my calculator here, selecting on the cell that has my sample proportion and my sample size in it. Other questions on this before we keep moving? Okay. So hit enter there. Now my lower bound is just take my sample proportion, subtract the number of standard deviations away I need to go to my lower bound. If that's the number of standard deviations away, I need to multiply that by what is the standard deviation, right? And once again, we want to copy this down. The only thing we want to change when we're building different levels of confidence is my z value, right? So the only cell reference here that I want to not freeze would be that z-value cell reference. Everything else, I'm going to go in and freeze that. Okay. So I'm going to also kind of cheat a little bit, not cheat, just do some shortcuts. So copy this. And I'm going to go and paste it. Right? I should have the exact same thing. But for my upper bound, I know I want the exact same equation. The only difference is I'm adding my margin of error. So I just go in, copy, paste that so it doesn't update the cell references, change my negative to a positive sign. Now I can copy both of these down. I should be getting 3 different levels of confidence relatively quickly. Notice at higher levels of confidence, I'm getting wider ranges. So my lower bound is getting a little bit lower, my upper bound is getting a little bit higher. Now with proportions, you'll kind of see that having these really large sample sizes, well, the variance of my proportions is p times 1 minus p. It's not going to get very large, right? And so having really large sample sizes, notice what did it do? It really drove down that standard deviation, right? So these insanely high sample sizes really drove down that standard deviation, which means I'm going to be adding and subtracting a small value to the left and the right. I'm going to be in these pretty narrow ranges, right, for my confidence interval, right? Which is good. Right? In this case, I could say, based off of these, major YouTube pages, the proportion of true population proportion of videos that are getting more likes and dislikes is, somewhere between 78.2 and 78.9%, and that's a very narrow range, right? So this kind of really highlights like having these huge samples, like 37,000 observations. I can make some really accurate predictions just based off of whatever I see from my sample. Any questions on this before we keep moving? So, anything else I want to say? Well, I'll just kind of work in the opposite direction just to prove this to you. Let's say I found the exact same information, but it was from a really small sample, right? So I still saw the same sample proportion, but it was just based on a sample of 100. What should happen? Well, if my sample size is getting smaller, what's going to happen to the standard deviation of my sample proportions? My denominator is getting smaller, the fraction is going to get larger. I'm then adding and subtracting a larger amount to that sample proportion that I found, I'm going to be getting wider intervals. So notice if I only had a small sample, but found the same information, now I've got, a proportion of my intervals are like 0.71 to 0.85. They're a lot wider, right? Which, not that they're completely unuseful, but like, it's a pretty wide range, right? If you told me, the proportion of people who were in favor of, I just looked this up the other day, legalization of marijuana in Indiana is between 0.3 and 0.8. Okay, I probably could have guessed and told you, right? But if I can say it's in between 0.57 and 0.59, that's a lot more useful, right? So sample size of 100 probably aren't going to allow us to really do that, right? But if we can get these huge samples, 37,000, man, I can really pinpoint down where that true population proportion is. Any questions on this? All right, I've got one more thing that I want to show you that I think will maybe, hopefully be helpful. Right? So, let's kind of go back a little bit. And I'm using an example here where we're going to go back to sample means now. Okay. So, I said earlier, right, we had this idea that if I had all these different sample means, like I just kept taking samples, if I built confidence intervals around like 1,000 different sample means, whatever level of alpha I choose to build those confidence intervals, that's the the proportion of confidence intervals that will include the true mean. So if I did 95%, that would mean that proportion of confidence intervals that I'm building that will include the true population mean will be 0.95. Now 0.05 or 5% of the time, I'd have a confidence interval that doesn't, but whatever alpha level I've chosen, that would kind of correspond to, having that level of confidence that my that proportion of my confidence intervals will include the true population mean. So I tried to build a thing to kind of prove this to you. So I had this data of these grades that people have gotten in my statistics class. I then found kind of what that true mean was. Right? So that's the true population mean. Right? I then also found the true population variance. So I've got the population mean, I've got the population variance. What I then did was take 1,000 different samples, each sample of size 50, and I'm going to set, I think when you download, or if this is on Canvas, I think when it downloaded, it was 0.01. So we'll start out there. So I've got everything I need, right? I've got 1,000 different samples. I'm going to build a confidence interval around every single sample, okay? So how did I do this? Randomly generated some numbers. It looks up the student ID and then puts their score in here. That part, don't worry about any of the stuff of how I got the samples. I'm not expected to do any of that, right? But you can like do this if you know, this is one of the things in Excel that would be kind of outside the scope of this class, but it is pretty useful. I can randomly generate some samples here. So I go down here. Here's my 1,000 different samples. I calculated the sample mean for every single sample, right? So I've got 1,000 different sample means. I'm then going to build a confidence interval around this, right? So for each one, I found the lower and upper bound. How did I do that? Well, I knew the true population variance because I had the population data. I can kind of cheat here. I had the population and sample data. I have my sample size. I can look up the z-value in Excel, right? I just did this all at one time. So this, I think, helps also show why I broke things down into steps earlier, because this is my standard deviation of my sample means, right? Before, I was just putting that in a different cell to make it easier. Now I'm just putting it all in one cell. Here is that z-value that corresponds to having half of alpha in the tail. Before, I put that in a different cell, so it made it a little bit easier. But I could type it all in at once, right? I could really consolidate that. I personally think it's just easier to make mistakes doing that. That's why I kind of show you how to do it the way I did before with the other examples. But you could do it all at once here. I then did the exact same thing, but added my margin of error, my upper bound, and I did that for every single sample. So I've now got 1,000 different confidence intervals for 1,000 different samples. What I'm then going to do is check and see, okay, look, if my true population mean is within this confidence interval, put a 1 in this cell. If not, put a 0. So we'll go back up just as a reminder. That population mean was 79.8. So every time it's in the interval, I get a 1. Every time it's not in the interval, let's see if I can find one. There shouldn't be a lot of them. Here, right, my true mean 79.8 or whatever it was is going to be a little bit outside the interval, so I get a 0. Okay. So what I then am going to do is count up, just using that sum function. I'm going to add up this entire row, which should add up to the number of confidence intervals that were a 1, or the number of confidence intervals that included the true population mean. And then I'll divide that by my total number of samples, which is 1,000, multiply it by 100 just to turn it into a percentage, which is what I did down here, right? And that's just telling me the percent of my confidence intervals that included the true population mean. Now remember, we had alpha set to 0.01, so hopefully what should be true is 99% of my confidence intervals should include the true population mean. Sure enough, I mean 98.9, it's not perfect because in theory we need like an infinite number of samples to prove this, but even with 1,000, I can kind of see like, even if I'm generating new random numbers and random samples, 99.2, 98.5, oops, 99.1, it's always going to be kind of hovering right around that 99%. Now, to truly show this to you, like I said, I need an infinite as opposed to 1,000 samples, and that's why it's a little bit off, right? I go back up here. If I then wanted to change alpha, right? Did the exact same process. If I go from an alpha of 0.01 to 0.1, right? That should mean now that 90% of my confidence intervals should include the true population mean. I hit enter, everything updates, and sure enough, oh, there we go. Here, I got exactly 90%, right? And it's going to vary a little bit as I kind of generate these new random samples. But I think hopefully this shows like you can prove this to yourself with data, whatever level of confidence I'm choosing, that's the percent of times my confidence interval will include the true population mean, even if I have a situation where I can't observe that population mean. Okay. All right, so you should have everything you need to complete that Excel assignment. That assignment stuff was all before spring break. If you have any questions, I got my office hours today, 2 to 4, and tomorrow, 2 to 4, or shoot me an email. We can find another time for to answer questions via email. Okay. All right, we'll see you guys on Friday.